Consider this closed loop control system that we have been discussing so far of the DC motor plant. We have designed the value of Nx and Nu. We know how to do that. We need to design the controller K. The controller is supposed to handle only the small signal values. See that here what is being fed back, the state xk is of two parts, containing two parts, the steady state part x and the xk hat, the small signal part, the deviations in the neighborhood of the steady state value. So it is this xk hat that is passed through the controller and acts as uk hat input, that is, it acts as the small signal control input to the plant. So if you consider only the control part will look like this, the highlighted, green highlighted part here. So this is the control part. So we can forget about the Nx and Nu, that is the feed forward part, when you are designing the controller gain K. Now let me set the steady state value to 0. So which means that the reference here for all the states that is fed back is set to 0. Which means all the states, in this case Ia and omega, are set to 0 value, which means eventually after some time has elapsed, the xk will reach the steady state value of 0. So if the dynamics works for the set point 0, it will work for any other arbitrary set point also. So setting x is equal to 0 is a very convenient set point. Without loss of generality, we can then now focus only on the dynamics of the small signal part. So when you now set this x is equal to 0, the control block schematic becomes much simpler. Let us just redraw that. So let us say that I will redraw it like this. Make some space. Yeah. So we will have this comparator. So you have this reference comparing with the feedback, and the error goes through the controller and the plant. You have the controlled output and the sensed states are fed back. So this is our control block schematic, and I'm going to set the reference of all the states to 0, and what is fed back xk is now only xk hat, because the steady state part is 0. On control it will become 0. So what you have here is minus xk hat. This is the controller k, and then after having passed through the controller, you have minus k xk hat. Now this will act as a small signal control input to the plant. So as far as the control aspect is concerned, the small signal control input, and the output of course is omega. So this is our small signal control aspect, and we can use this simplified block diagram to find out the value of k. So if I take this system state equation, it is written as xk plus 1 hat, small signal only, axk hat plus buk hat. Now uk is this, replace it with minus kxk hat. So if you do that, so you have axk hat b, uk hat will be replaced by, now I'll put k xk hat here and I'll put this minus here. So this becomes our new state equation under closed loop condition. So xk plus 1 hat becomes a minus bk xk hat. So this becomes the closed loop state equation, and a minus bk becomes the characteristic matrix, and the eigenvalue of that, or the roots of the characteristic equation of a minus bk, are nothing but the closed loop poles. So if you find out the roots of the characteristic equation of A minus BK, you will obtain the closed loop poles of the closed loop system. So this is what this matrix A minus BK is what we will utilize to find the value of K. So we decide where we want to locate the closed loop poles of the system, and once we decide where the desired closed loop pole locations are supposed to be, then K is the only variable, only unknown variable, and we can determine that. So we will see how we go about doing this. A minus BK is the system matrix for the closed loop system, and let us look into this matrix. Let us dissect it and look at the component elements of the matrix. So let me write that down. So we have A minus BK, and if we have to get the characteristic equation, we need to get the determinant of Zi minus A minus BK, basically the eigenvalues, the roots of the characteristic equation. So for that, you have to first have the characteristic equation. So Zi minus A minus BK will give you the characteristic equation. The roots of that will give you the closed loop pole values. Now let us take our example of a two-state system. We have discussed the DC motor example, two states, IA and omega. So for the two-state system, A is a 2 by 2 matrix. So let us form this characteristic equation. So Z I is again a 2 by 2 matrix, identity matrix, minus A. So I will put variables there, A11, A12, A21, A22. So this is the 2 by 2 A matrix of the open loop system, and B is column vector B1 and B2 for one control input, in this case which is VA, the armature voltage, and then the controller gains K. So that I will write it as a row vector like this, K1 and K2. So you put it down in this fashion. This is a column vector, this is a row vector, so that the dimensional compatibility is maintained. So determinant of this entire set is like this. So if you further simplify, I will quickly write that down. This is Z minus A11 and plus B1K1. So on the next you have 0 minus A12 plus minus or minus B1K2. Then here you have 0 minus A21 plus B2K1. Then here Z minus A22 plus B2K2. So this is a 2 by 2 matrix. Determinant of this will give you the characteristic equation. Now that has K1 and K2 as the unknowns. So it will be of the form, because it is a second order system, Z square plus alpha 1 Z plus alpha 0. Alpha 1 and alpha 2 are functions of K1 and K2. So they contain K1 and K2. This is one part. So starting from the A minus BK, finding its eigenvalues, we have landed up with this characteristic equation. Now let us say, let me take the Z plane. and let me do this pole placement. What do I desire? I desire the two poles that I have to place, closed loop poles. Let us say that I want to place it at this point. So means that the roots of this equation should lie here and here. So these two poles, the desired value or location of this closed loop poles, lambda 1 and lambda 2. So going from this side, I know the characteristic equation will be z minus lambda 1 to z minus lambda 2, because they are the roots. So this is the characteristic equation, and this will turn out to be z square plus minus lambda 1 minus lambda 2z plus lambda 1 lambda 2. So now you look here, the power of z, alpha 1 is this. I can equate, I know lambda 1 lambda 2 because I have chosen lambda 1 lambda 2. I have placed what should be the desired closed loop pole location. So lambda 1 lambda 2 known. This has two unknowns k1 k2. Likewise, I have alpha naught having k1 and k2, and then I have this lambda 1 lambda 2. So I have two equations, two unknowns, and I can solve for k1 and k2 and get the controller gain matrix, knowing the values of a, b and c. So this is the process that we would go about in trying to find the values of k1 and k2, the controller gains. But how do we do this? It is cumbersome even for a 2 by 2 matrix. So if there are a very large number of states, it can become difficult to do by hand. So there are algorithms. There are two algorithms. One is Acker. Both in MATLAB and Octave, you will see this Acker, and even in Python, Acker, coming from Ackermann's algorithm or Ackermann's formula. The second one is Place. So this Place is also another roots finding algorithm, where you give the desired pole location, you will obtain the values of k1 and k2. So both Acker and Place are pole assignment tools, and you can use that. Acker can be used for a small system, small order system, and here even identical closed loop pole locations at same point is also allowed. Whereas Place is more accurate and has capability to handle very large number of states. But this cannot take identical pole placements. So you may have to displace the poles slightly by some decimal points. Let us now go back to writing the script file in the .m. See, we have already started writing the script in the full state feedback design.m file. So we have incorporated the design of the NX and NU matrices. We will continue in this forward to design the value of k, the controller gains. On the right side, you have the Octave window, Octave environment open. Keep it open so that we can test some syntax as we go along. So let me put a comment line, and then let me say design of the controller k, and let me underscore that and start the design of the controller. So I will leave some space there and then say PC. PC is the closed loop pole location values that I would like to enter. So here I am going to use the input command, enter the row vector of the desired closed loop pole locations in this format. Open the square brackets and then enter it. So this will actually ask in the Octave window to enter the row vector of the desired closed loop poles. So you will give appropriate values which are falling within the unit circle so that they are stable. So we will use that and then design the value of k. So as we discussed, I have as inputs the A matrix, the open loop A matrix of the discrete system, the open loop B matrix, and using these two, A minus Bk is actually the closed loop system dynamics. K is the unknown, and I am giving here a vector of desired closed loop positions, which is basically the solutions of the characteristic roots of the A minus Bk matrix. So giving these three inputs, I should get the value of the controller gains. I have used here Acker. As I said, you can always find out. You can say help Acker. You will get the syntax and the description of that. I also said that there is another algorithm. I'll clear the screen. You can say help place. You can use place. Place is much more powerful, much more precise, and much more useful for multi-input, multi-output, and larger systems. So you can go through this syntax. So I have used Acker here, but you can as well use place with the same input syntax. You can see that in place also I could use the same A, B, and the closed loop pole location vector, and you will get an output. Here they have used the F as the controller gain matrix. So here we are using K. So let us proceed further. Let me clear up the right side window. Yes, and coming back to our scripting. So you have now found the value of K. So closed loop response. Let us try to find the closed loop response. I will use the initial function. I'll use this initial function, and to the initial function I will input A minus Bk. A minus Bk is the system dynamics, so that xk plus 1 is equal to A minus Bk into xk. There is no input, zero input. So the closed loop state equations input matrix is 0, and C and D remains the same. Ts is the sampling time. So that whole thing is represented in the state space form. So that is one aspect. What is the system? You can always use help initial here to see what is it that we are doing. So I am giving the system. So this whole entire thing, system in the state space form, and then I have to give the initial values. So I want to deviate the states above or below 0. 0 is the steady state value finally, because I am not giving any reference. Just giving all states set to 1. Finally, all states will have to decay to 0 because we are giving a reference of 0. The output will be the y, the output, t is the time value, and x is the state values. So then we display, let us display the gains k. What is the gains k that we have used here? Let us display it so that we know what it is. That is the gain vector that is used here also. Okay, I'm converting number to string and then displaying it, and then let us plot, subplot. So I'm going to see two plots at a time. So subplot, I'm also setting axis so that I don't want a change of axis when the plots change. I'm holding the axis, and then states function t comma x means it is plotting the states. All the states are plotted. X label time, y label states. Okay, so this is one plot. Another plot 1 comma 2, I will maintain the same. Now here I am plotting t minus kx. Minus kx is nothing but the input u. So you see here minus kx is nothing but the input, and we can observe the input. We observe the states, all the states, and we can observe the input u. Going back to the script, I will continue. So x label, y label is the input. So this will be the one that is plotted, displayed. Now we want to iterate for different positioning of the closed loop pole positions. I can change the closed loop pole positions. I can get a different value of k and see how the response changes with these different values of k. So this, therefore, you need to put it into a while loop and end while. So this whole set of statements will be within a while loop. So there is a string compare flag y. So let us set flag is equal to y, and as long as flag is uppercase or lowercase y, this loop will be executed. So we need to ask a question here. So let us ask a question. Do you want to modify or tune the controller? Yes or no? Based on that, the flag will be set or not set, and then whether you want to exceed the while loop is decided here. So this will complete the design of the controller. So you can iterate it any number of times and see the outputs, the response, and accordingly freeze that value of k, which kind of satisfies your time response. Now let us run this and then see how it looks and how it executes. Before we execute the script, remember that we are setting the reference. All the states, the reference value is set to 0, which means that ultimately all the states in the plant will finally settle down to 0 in the steady state. So keep that in mind and let us execute the script that we have just written and find out the values of the controller gain k. Coming back to the Octave script and also the Octave environment, let me clear up the Octave environment. I have used the CLC command, and here I will call this design script file, full state feedback design.m file. So I am in the appropriate directory here, you see, in the control examples directory, and let me call it full state feedback underscore design. So when I execute this, it will do all these, right from loading the package, loading all the packages, clearing the screen, calling the DC motor function script, where the DC motor, the plant is designed. It is a two-state system, and NX and NU will be designed, and then the controller will be designed. So let us go through that. Let's see what happens. So when I executed that, you see the values, the DC motor parameters, all these are set, which are actually set here. And you get the value of NX and NU. So this is NX and this is NU. And then you are at this point, it is waiting for you to give some inputs. Enter the row vector, the desired closed loop poles. So we are in the digital domain, and then we need to enter the closed loop poles. I know that all the closed loop poles should be inside the unit circle for the system to be stable. So I will give some poles which are within the unit circle. So let me give 0.5, and I have to give one more, and that is minus 0.5. So I am giving two poles, 0.5 and minus 0.5. I can give infinite, there are infinite possibilities. I can give anything within the unit circle. I can also give imaginary poles, and I can also give real poles and combinations. But they have to be within the unit circle. So it is actually a problem of riches. You don't know which one to choose, but that is another problem where you use some optimizing criterion to decide what should be the value that I should give. But for now, you can place anywhere. So you see here the gain that is calculated is the gain vector. For one state, the state IA, the gain value is 38.98, and for the omega it is 133.192. Let us ask the question, do you want to tune? So in the meantime, you see what is plotted here on the figure window. So up here you see the states on the top plot. X-axis is time. So you have two waveforms, one in red, there is one state, and then the blue is the other state. And on the bottom, you see the input minus kx. So that is the input. Finally, input is also settling to 0 because all the states finally settle to 0, the steady state value, because we are given reference as 0. So if it works for reference 0, it will work for any other set point references also. So let us say that we want to do some iteration. Observe the input value swinging from around minus 150 to plus 150. Now let us change the value of the closed loop pole locations. Let us place the closed loop pole location closer to 0 and then see what happens. Let me modify. I want to modify, so I will say yes, and then we can give a new closed loop pole location. Let's see what happens if I give 0, 0. I can give identical closed loop pole locations using the Acker formula. If it is placed, you can give 0 and 0.0001 so that they are not identical. Make it distinct. So with Acker, I can give 0 and 0, and on entering you see that the gains, I have a new set of gains here, and here on the plot we'll see that the states have stabilized and gone to 0 within the third sample. But you look at the input has gone to 200 points. So which means that as you start going closer towards 0, you will see that the input is larger and the response is faster and quicker. Let me exit the while loop, close this. I will remove the restriction on the axis, so let the axis auto adjust to any value. So I am removing the restriction on the axis limit. Let us save that, and I will execute the script again, and this time I will give the value of the desired closed loop pole location that is more closer to the unit circle. I'll say 0.8 and minus 0.8, more closer to the unit circle, and I expect that it will be more oscillatory and the time taken will be much longer. You see that the states finally settle to 0 probably after 0.5 seconds. So likewise, the input also takes that much amount of time to bring the states to its final steady state value as set by the reference, which is 0 in these cases. So you see that as you one kind of intuitive rule would be that when you place the desired closed loop positions within the unit circle, the closer you place the poles to 0, faster it is going to be, and quicker is the settling time, and larger will be the control energy which you would see at the input. As you start moving the closed loop pole placement locations more closer to the unit circle, it will be oscillatory, settling time will be longer, but on the other hand, the control energy will be lower, smaller. So this is the general intuitive feel that you can take away from here. But when you do optimal controls, you have another formal strategy for deciding the location of the desired closed loop poles. Before I close this session on full state feedback, I would like to show you the Python script also. I have already written this Python script. It is the same concept as we used in the Octave scripting, finding the value of nx and nu, and then going on to find the value of the controller gains k. The concept is the same. The syntax only will vary, which you may have to kind of adapt to the Python syntax. So let me explain to you in brief. This may appear to be a long script, but essentially it is having one-to-one correspondence with what we did in Octave. So let me have a blank sheet overlay to bring in focus and then make it easier for you to understand. Let me use this blank sheet and try to explain this Python script to you. So this part here, as you see, this part here is importing the modules, the various modules, which we have already seen the earlier Python script while discussing root locus method. So you import NumPy, Matplotlib, controls, OS, and myplant.model. So this is where the motor model resides. Okay, I will show you that shortly. I have that here on top, my models file also. So let me go a bit further and then show you the scripts. So the next part is to actually get the plant model into the environment space. So you clear, and then we set the sampling time to 0.02, and then set the parameters, the RA, LA, B, all those things, RA, LA, KT, B, and J, and pass those parameters and call the motor model. This is the DC motor model. This is very similar to what we wrote for the root locus controller design too. So this DC motor design model, what is it? How does it look like? So this basically is what is called, it is calling the modules myplants.models, and within that is the DC motor function. So let me go there. I have this models.py. So let me click on that, and you see that this is about the plant models, where you import NumPy and control. The function definition is like this: DC motor, you pass some parameters and the sampling time, and very similar to what we wrote during the root locus design discussion. So you set the parameters. So from the parameters you pick off RA, LA, KT, B, and J, and then the small signal model comes in. So AC, this is the continuous domain A matrix, RA by LA, KT by J, KT by LA, and minus B by J. Then the B matrix, C matrix, exactly similar to what you did in Octave. And then the continuous domain model of the plant, sysGPC, is CTL. You are calling the controller module. You are using the SS function and say that AC, BC, and VC, you are only taking the first column as the control input. The second column represents that corresponding to the torque, load torque, which is considered as a disturbance, CC and DC. Okay, so these are the matrices. So let me push this aside. Then you discretize the plant. So for discretizing the plant, we sample it as we did before using the zero order hold method. So the continuous domain plant is sampled with sampling time TS with the method zero order hold. And you get the discretized version of the plant in this fashion. Okay, so this is what you pass it out, sysGPD. And going back again here, then bringing your attention back to this point here. So I am getting AD, BD, CD and DD, discrete domain ABC matrices from sysGPD, which was the result parameter or the output parameter of the DC motor function. So now you have the model of the plant ABC matrices. From there, we start to find the values of NX, NU, and then K. So let me focus on NX, NU. So this is essentially the same thing like in Octave. As I said, syntax is different. In Octave, writing matrices is very easy. But in Python, you need to use this horizontal stack, H stack, and vertical stack to place the various matrices. So AD minus I is the first matrix that you place. Here it's a 2 by 2 matrix. Then you have BD. This is the controlled output, and the null matrix here. M is the null matrix and identity put together. Then we need to find NX and NU. So so once this matrix, AA matrix, is placed in place, then you the M matrix, which is this, has been put in place. We use the vertical stack, zeros and the identity, and then obtain the NN using the equation, which is AA inverse into M. So that's what which is done here. Then you are decomposing the NN matrix into NX and NU and print the NX and NU matrix. So this is about obtaining the values NX and NU. Then finding the controller gain K. So we set the time axis 0 to 2, TS is the sampling time, and then we go into the while loop as before. And in the while loop, you see here, this is the placement of the desired closed loop pole locations. So that is what you will be giving. In this case, we are giving 2 closed loop pole locations, the second order system, and then we use the Acker function from the control toolbox and obtain the value of K. You are passing in AD, BD and the desired closed loop pole locations. AC, the closed loop dynamic matrix, is calculated, A minus BK, and then the closed loop system, and you find the initial value response. So the initial value response, where all the states are set to ones, and you get T and Y, time and the y which is containing state 1 and state 2. So we will print the controller again and then have the subplots. So one subplot will print both the states, current and the armature current and the omega, y0 and y1. 2 at disturbance. The disturbance is that we have disturbed it from 0 by saying that all the states are at value 1. The steady state has to be 0 because the reference is 0. So ultimately all the states will settle down to 0. Then the second subplot is minus ky, which is the input. And then we see, so this is the syntax for that. And then you iterate the loop. So this is basically the Python script. We can execute it. Let us execute that. So let me go to the right part. So I can remove this. So now I will go here and call IPython. I am already in the proper directory. You see here control examples. Okay. I call IPython. So I'm in IPython. I run. So this is full state design.py. So that I will say and then execute it. So on execution, you will get the same ABCD matrices that you did in that you got obtained in Octave scripting. NX and NU matrices 2, 1, 4.1, both same. So let me give this 0.8 and minus 0.8. This is one of the last examples that we did in using the Octave scripting, and you could probably see the results. This is the controller gain, and so you see here the input energy between plus or minus 40. So you have the two state variables, the speed and the IA, settling down to 0, the final steady state condition. So very similar to what you obtained in Octave, executing the Octave script, only that the Python script has a different syntax. Okay. So this is how you could use even Python for doing your controls.